Okay, hi everyone, and welcome to our Friday class. The people are saying on the chat that the YouTube had a problem. There was some problem with the thing upstream of that, but it should all be good now. You may have to reload, but it looks like everything's fine. I can see that there are 14 people on YouTube already, and I can also see that people are watching on Twitch. So it should all be good. Welcome to the lecture, and those of you who have been paying attention know that today's a very special one. We've got a guest lecture, and our guest lecture today is Dr. Pascal Bircher, who's an AI expert who is in our school. And I mentioned to you before, one of the privileges of studying at a university like ANU is you have all kinds of amazing experts around, and one of the things I enjoy in my class is being able to invite people like Pascal to give guest lectures. And today's guest lecture is broadly about AI, and more narrowly a little bit more about how you might write an agent to play a game. I think with that, I'm going to before I do, there's two more things I want to mention. First of all, Pascal's background. More narrow background. Some of you think of AI as some big mysterious monolith. Pascal's background is in the area of optimization and planning, which is a specific sub-discipline within AI that, of course, is quite relevant, as if you can imagine from the very highest level description, is quite relevant to the problem you're going to be solving if you're doing the 1140 assignment, and that is how you solve a game problem. You've got to plan your way through the problem. It's an optimization problem, of course. But he can talk more about that in a short while. The other thing is, those of you who paid attention will notice that Leo has written at the top of the lecture note in the chat that there is a poll. Don't do the poll yet. You don't need to do the poll yet. Pascal is going to tell you when to answer the questions in the poll, so just hold off. Wait up until it's time to do the poll, and when he asks you to, you can do that poll. Now, I think without further ado, I'm going to flip over to, hopefully all this technology will work. I'm going to flip us over, wait a second. First of all, I want to show you that slide, so you can see it's Pascal who's going to be talking, and now I'm going to flip over to Zoom. And we can see Pascal's slides. There's Pascal's slides. We can't see his face just yet, but this is via Zoom, and you can see Pascal via Zoom. And without further ado, I think Pascal's now live on audio. Can you hear me, Pascal?
Yes, very clearly. Thank you.
Perfect. Okay, so without further ado, I'll hand over to Pascal, and I'll mute my mic. One last thing. We're going to do questions via the chat. And what I suggest you do is, I will try and aggregate questions on the chat and feed them through orally to Pascal. Okay? Without further ado, Pascal, the lecture is yours.
Yeah, thank you very much. Okay, then let's just start into it. And of course, the mouse doesn't work. Now it does. Okay, so that's just very briefly the overview of today's lecture. The one thing that I will focus on is in the middle. That's the Minimax algorithm and an extension alpha-beta pruning. That will be the main technique that you're going to learn today, which I'm going to explain in quite some detail. All the rest will just be additional background information. So regarding the motivation, why we should study games in the first place, obviously, it's for game AI, either for modern computer games, but also for computer game adaptations of board games. So simply, if you implement the board game on the computer, then you still might want an AI. So obviously, that's a reason. Okay, but also just for the sake of knowledge itself. If you don't know the game of Connect 4, here you put pieces in the top row, and then they fall down. Two players take alternating turns, and you must get 4 of the same color, either in a diagonal, in a horizontal, or in a vertical line. And the game doesn't sound too hard. It looks like there are not that extremely many states, and you just would like to know, can I actually enforce a win no matter how my opponent plays? And yeah, this technology can answer that question. But also because many real-world problems can be regarded a game. And there, the other players in the real world, the other agents, can just be regarded other players in the game. Examples are robotics or multi-agent planning, although here, normally, the agents are regarded as partners, so they work towards one cooperative goal. But in that lecture today, we focus on antagonistic games. So we are just playing against somebody and not together with other players. And a very big topic for game theory is economics. And I'm not going to details here. I'm just saying it's really, really interesting. And there is a lot of easy to digest background information, for instance, on the Nash equilibrium and also on the prisoner's dilemma, which is really easy to understand, really interesting. So if you have a couple of minutes, just Google for game theory, or in particular, the Nash equilibrium and the prisoner's dilemma. I think that's really interesting. So what are games? Games consist of at least one player. Normally we have two or more and a set of moves for each players. And given the strategy for each player, we can determine the payoff of the entire game. So essentially a game ends in a certain way if we know how every player behaves. And strategies, by the way, are also called policies, and the final outcome will then be called payoff. And there are different kinds of games for which I have prepared that online poll, of which sadly a few of you already answered a few questions, mostly one. So let's talk about the required definitions for that online poll. You can have either perfect information, that's if you know everything, if you see everything and you know everything. And you can have imperfect information. For instance, cards of your opponents can be hidden. Well, obviously, you can have one player, two players, or more. If you have more than two, then it's regarded a multiplayer game. There are zero-sum games and non-zero-sum games. So a zero-sum game is if everything that you win must be from the losses of the other opponents. So it essentially means if I win, then the others lose. And if the others lose, then I'm winning. It's a little bit more complicated if there's more than two players, but the principle still holds there. And games can involve chance, randomness, or they can be completely deterministic. And yeah, at the bottom you see a few games, and later I will ask you to do the online poll for this. So a strategy tells you how to play a game. And formally, this can be represented as a tree, as you see on the right in the game tic-tac-toe. So a strategy is essentially telling you for each single state which move you're going to select, which you see here with the bold arrows. And because pretty much every game can be represented as such a tree, you can also do search on that tree. So if the tree is small enough, then you can even derive an optimal strategy by just searching within that tree. So what are we looking for when we try to solve games? At the one hand, we can be interested in game AI, and maybe even in differently strong game AIs. We could be interested in one that's really weak, one that's quite a challenge, or one that's even really completely strong or even unbeatable. But that's still not the same like the game theoretic outcome. And the game theoretic outcome assumes that all players play rational. And playing rational means that they optimize their expected reward without assuming that there are any collaborations. So every player tries to win, and they do so by choosing the optimal move, by optimizing the expectation of everything. And if we know the outcome of a game based on these assumptions, then we say it's solved. Okay, that's different from having a strong AI. It really means we know whether we can force or win. And well, just because we have an AI that can never be beaten doesn't really mean that the game is solved. Okay, so at this point, I would like to make an interruption for exactly 5 minutes. So please open the poll now. And you can start answering the questions now, because, well, you know all the definitions now. And in 3 minutes or so, I will just show you some statistics of how everyone has done. So don't take too much time. I thought about 30 seconds per question. I mean, you really just have to check. And it's also telling you the right answers. If you have questions about this, there will be time, well, either in the forum, obviously, I can still answer questions there, or also later at the end of this talk when we have a couple of minutes for questions. But to stall a little bit more time, so that those of you who are already done are not bored, I'm talking a little bit about one interesting thing that I found while creating that is the difference of partial observability and randomness. So in the game Scrabble, for instance, which is the second, let me just check. Okay, some of you have already answered the second question, not all of you. In Scrabble, for instance, you have, after each turn, you have to draw a tile out of a sack, so you don't see the tiles. And that really raises the question whether this should be regarded only partial observability, because you just don't see the tile that you're grabbing, or whether this should be regarded a random process. Because you could also simulate this like throwing a dice, and then depending on the outcome, you take a respective tile. And although it looks like partial observability because the tile is just hidden for you, I would argue that's actually a random process, because you really want to get a random tile. So sometimes you just have to think about this a little bit more carefully. Okay, so we have 2 minutes left. So maybe if I started talking about Scrabble, let's just continue. For Scrabble, for example, there are also very strong AIs available. But the game is still not regarded solved in the sense that it's really know whether there is an optimal strategy. Or no, that the optimal strategy is not yet known, or at least I think so. Actually, I did not take a too close look into the game of Scrabble. I'm more interested in the game of Go and chess, for instance, where I will say something about later on. Okay, it seems like most people are through, and most questions are actually read. So the statistics are that in chess, 30% of you got the right response, which is pretty cool. And for the rest, it's pretty much about 15%. Tic-tac-toe obviously is much better. That's great. So in tic-tac-toe, 70% of you got exactly the right response. And the third game, I think that's poker, 55% got the right response. I can actually show you the statistics. We have 1 minute left, so don't worry about the lost time. Yes? Yeah, go on. Okay. Okay. Yeah. Okay. So with roulette, I've actually added a note. I actually did not research about that, so that might actually be wrong. But I put this actually into the notes. I just said, well, the probabilities should pretty much be known, and I believe I don't even know the game in much detail. So I don't think that you have to plan ahead for many moves. I think you're just betting against the outcomes, and I think you know pretty much the probabilities. But with regards to the other two questions, so zero sum means that the entire outcome of the game will always add up to 0. So when you have a two-player game and I win, and the only way of me winning is that the other one loses, then it's zero sum, because I win, the other one loses. And if there's a draw, then nobody wins. So the outcome, the sum of the outcome will still be 0. And in the example of roulette, that's also zero sum, because if I win something, I win it from the bank. But if I lose something, then the bank will win exactly my amount. So that will still be zero sum. The same holds for poker. Okay, I think more questions can be taken at the end. I need to continue. So Minimax is now a game not a game, sorry, an algorithm by which you can search in those game trees that I've shown to find this winning strategy. And in that game, Minimax, first we consider only 2 players, and we name the first one Max. That's the player that starts the game, and the other one Min. And they're called that way because Max wants to maximize his own reward, whereas the Min player wants to minimize the reward of the Max player. So essentially both want to win, but Max wants to maximize his own and Min wants to minimize the reward of Max. So they're perfectly symmetric. And this is the algorithm that searches in such a game tree. And you have alternating layers of Max and Min nodes. And whenever the current node is a leaf node, which means that there are no actions or moves applicable, then you just return the payoff, right? It's a final situation. You know whether it's won or lost. And then you can return that respective value. And if it's not a leaf node, if there are moves, then you're iterating over all successors, and the maximum node or the max player will maximize over all the outcomes. But because the children of a max node will be in the nodes in which the min player does its move, we will choose the maximum over all successors where the successor value is determined by the min player. And for the min player, it's completely symmetric. So the min player also iterates over all successors, but the values of the successors are evaluated using the function on the left from the max player. So there's a simple example. In this game of tic-tac-toe, I'm assuming that everybody knows how it's playing plate. Max player is X, and we don't know the final outcome, which I've indicated by those question marks yet. We generate all successor nodes, although the right ones are not really generated yet because we are searching in a depth first search. So I really just showed all of them so you see that they are there. But we start with the left one. So only the left node is actually generated now. It's not a leaf, so we continue to expand it. So there are 2 new successes. For the left one, we know its outcome. It's a final node, and we know Max has lost. So the outcome is -1. So we continue to the next child of the min node. That child is also not a leaf, so we expand it. We know the outcome, that's a tie. So the value is 0. So we propagate it upwards. And now we know the values of all the childs. So now we can evaluate this as well. We go to the next child of the parent, and we go again to the next child of the parent, and so on and so on. So we do this depth first search until we've generated all the nodes. So we were able to propagate all the values upwards. And here now you see that we have shown that Max can enforce a win, which is quite obvious in this case because he only needs to set the X on the rightmost column, and then he wins. And for every node, we know how to play. But if we take a look at the space and time requirements of this algorithm, then we see that it's actually quite expensive because we just had to visit every single node in the tree. And so we want to know how big can that tree be. And for this, we need to know the depth of the tree, that's D, and we need to know the branching factor. And the branching factor B is the maximum number of available moves per node, per state in which you can end up in. And such a tree obviously has an exponential size. So it's b to the power of d. And that's quite something. Remember, b is the branching factor, the number of moves per state, and d is essentially the game horizon. So if the game can take 100 moves, then you have the branching factor up to the power of 100. It's quite large. But space looks a little bit better Because we conduct a depth-first search. And because we conduct a depth-first search, we only need to store the longest path of the tree, not the entire tree. We can always forget already visited paths. And therefore, we only need to store one path at the time. And therefore, the space requirement is linear, which is much better, obviously. So, because Minimax suffers from the problem that we have always exponential runtime, we want to make it better. And we do so by alpha-beta pruning. And alpha-beta pruning exploits two variables, that's alpha and beta. And alpha stores the best value for the max player, and beta stores the best value for the min player. Because the best outcome for the min player is small, beta always stores the smallest value, and for alpha, vice versa. So you've just seen before that the outcome values, those are the V values, they are propagated upwards. And the alpha and beta values are propagated downwards. So you see this in this algorithm here, which is really just a very minor adaptation of the Minimax algorithm. And here you see that in that loop where we iterate over all the successor children, we always test whether the current outcome, I'm focusing on the left side of the max player, is better than the best move of the min player. So now think of what that means. If the max player has its turn, so the max player wants to choose a good outcome, but we have just explored a child which can guarantee that the outcome from one of its children is better than the best value that the min player can enforce, then we don't need to continue. And therefore we can return the V value right away. That might still look really, really abstract. Even I am having a little bit problems in understanding this abstract code, the intuition behind. So don't worry about this now, but instead focus on this example, which I hope explains it a little bit better. So let's take a look at the topmost node first. We start with the leftmost branch. So the topmost min node enters the leftmost branch and propagates the initial alpha and beta values, which are -infinity and infinity, downwards. And let's say we have explored the entire search tree on the left, and we found out that the value of that search tree is 5. So that 5 value gets propagated upwards to the min node. And that means that beta will be updated to 5, because we know that beta, the min player, can enforce a value of 5 by playing the left move. So we tell this to the max node below. Now it's the max node's move, and he investigates the leftmost sub-branch. Let's say we find out that the value is 2 there. So we propagate that 2 upwards to the max player. And therefore, alpha is updated to 2, because we know the max player can enforce a strategy, a game, with the outcome of 2 by playing the leftmost action. But when we investigate the second available move in the middle, and let's say we explore that entire search tree and we see, hey, cool, alpha can actually enforce an outcome of 7. Then we know that we do not have to continue to explore the other children of max, because we have beta equals 5. Beta equals 5 means the max node knows already that beta can enforce an outcome of 5. So why should max care about finding an even better value than 7? It could still find an outcome of 10, maybe even 10,000, but it doesn't matter, because even the 7 is sufficient to know that the min player will never choose the action in the middle. The min player will choose the very left action, which will lead to an outcome of 5. Therefore, max will never have even the opportunity to play his move that leads to 7. And that's the core idea behind alpha beta. So you have to take a look at the code from before, but also at this slide. I think this explains it very well how it works. I hope. Okay, just very shortly, an example in tic-tac-toe. Here I have given the initial values of alpha, beta, not to minus infinity and infinity, but to -1 and 1, simply because that's actually the minimum outcome and the maximum outcome that we know already. Right? We can either win or we can lose, and we've represented that in that game with -1 or 1. So we could simply set those values. In principle, for the v variable, we could do the same. So we could also improve v from -infinity to -1. It really doesn't make any difference at all. So I've given both. It really doesn't matter. So again, we expand this node here. We get 3 successors, although again, we do not really create the rightmost 2 successors. I just gave them to let you know they exist in principle, but we're not starting with them yet. We are conducting a depth-first search. So we are only producing the left node, the leftmost node. And we are propagating the alpha beta values down. So it's not a leaf, so we continue expanding it. The node 3 now is a terminal node, so the v value gets propagated upwards. And now, for the first time, we have the situation that the current v value is smaller or equal than the alpha value, and therefore we do not have to generate the second successor. So we've already saved 2 node expansions. So now we propagate this result back up, so we can now update the v value of the root node, and therefore, let me see. Oh no, okay, this stays the same now, but we've updated the v value, and now we go down to the next child. That's again a terminal node. So we know the value, which is v equals 1, and so we propagate this upwards to the root node. And the alpha value also gets updated. So you see here that before the alpha value was -1, but now we update v to 1, and therefore alpha is also updated. And now we can prune yet another time, because v is greater or equal than beta. And therefore, again, we know that we do not have to investigate the other children of the max node. The intuition is simply, well, we know already that we have found the maximum outcome, so why should we bother exploring more nodes? We already know that we have achieved the best result possible, so there is no need to continue. So you see here already that we have reduced the search tree quite significantly, and only by propagating alpha and beta values downwards the tree. So with regards to runtime or space requirements, in the worst case, we didn't win anything, because in the worst case, nothing can be pruned. But on average, something can be pruned. I still didn't get write down the complexities because I'm not explaining where they come from due to lack of time. But the point is that you can, in practice, pretty much always prune somewhere. So obviously, you should always do alpha-beta pruning because it can reduce the size of the search tree quite significantly. So in the game that, yes, sure. Yes. So when you go back to the algorithm, you see, do you actually see my mouse cursor? Yes? Okay, perfect. So when you take a look at the algorithm, you see here that the max player, well, obviously wants to maximize its reward, right? So the current value of v is always the maximum of the last value of v and the value of all successor nodes. But whenever we have that the v value is larger than the best value of the opponent, then we can immediately return that. Actually, it's, yeah. But if this is not the case, then we continue the search, and therefore we update this alpha value here. So alpha will then just be set to the current value. It's the maximum of the last alpha value and the new v value. And if you take a look at this line here, then you see that when you call the successor states, you're calling this other function. You call the function of the min value with your current alpha and beta value. And, and for the min function, it's exactly the same. The function for the min node, it also generates successor nodes, and then it calls the max function again. And it does so again with the alpha and beta values. So you're always passing down the alpha and beta values, the tree, based on what you've computed before. And this is what I've illustrated here, that you have your alpha and beta values and you're passing them down the tree, but they're not passed up again. You're only passing up the v value, which you also see in the algorithm, because you're only returning the v value. You're not returning alpha and beta values. The alpha and beta values are only put into those functions, which are only called for the children nodes. Okay. Awesome. Okay, randomness. So far, we have only taken a look at games with 2 players, and every player wants to win, right? And therefore, one is maximizing, the other one is minimizing. But what if you roll a dice or have other sort of randomness? And we can still represent this with such a game tree. But if you're incorporating randomness into the game tree, then you need to know how to compute the values. Because, well, we have just computed the values based on either taking the minimum or computing the maximum. So what is a min player? Is that also a maximum, or is it a minimum, or something else? Clearly, it's not a maximum, because if the other random player would be a maximum, then that would mean that the randomness would play in our favor. And it's not. Randomness is just something, but it's not always the best outcome. Minimum would be too pessimistic, because if the random player would be a min player, that would mean that the randomness would always choose the worst outcome. And that's also not the case. You're not always throwing the dice in the worst way possible. But instead, we want to play rational, and that means that we are maximizing the expectation. And this means that the value of a random node is the sum over all outcomes, but the outcome will be multiplied by the probability of that outcome. So you see this in this extended Minimax tree, which incorporates for randomness. So in this example here, I was assuming that every player does some move, whatever that might be, and directly afterwards you throw 2 dice. And what you're being interested in is the outcome of the sum of the dice, just in this game. Okay, I just say in this game, I'm interested in the sum of the outcome of 2 dice. And if you throw 2 dice, obviously the outcome can be 2, 3, 4, and so on until 12. Obviously, the probability for the outcome of 2 is only 1 in 36, because both dice have to be a 1. Symmetrically, you have the same for the outcome of 12. The probability is 1 to 36. And for the outcome of 7, it's more likely you have 6 to 36. And the outcome, so that's the probability that you need to take into account. And you sum over the probability times the value of the node. And the value of the node is exactly the same way as we did it before, because now it's the turn of the opponent, right? So it's either a min value or it's a max value. So you use exactly the same algorithm that you've used before, just extended to this random decision. Okay, I have called the last 2 sections solving small games, because I said that the tree that we built and the algorithm that we have discussed before bases directly on that tree is exponential. And you cannot solve all the games perfectly if they grow too large because of that exponential size. So we need to know, what does large mean? When is a game actually too large to be solved, so that we can still construct the entire game tree? So I've just provided a few examples, just so that we get some intuition on the actual numbers that you can see. I don't know what large means. Let's start with a simple game, tic-tac-toe. So this is just a rough estimate on the number of possible game states. Keep in mind, there are 9 different fields or cells in one board, and every single position can take 3 values. It's either empty, or it's an O, or it's an X. So clearly, a very, very, very rough maximum of possible board games is 3 to the power of 9. That's obviously a very rough estimate, for instance, because it includes invalid states. For instance, the board in which there are only X's. That's clearly not possible. And the actual maximum, which you can find by just writing a trivial computer program which does breadth first search, the actual maximum is roughly 5,000. But you can even do better by eliminating symmetries. Obviously, you can rotate the board, and then different situations suddenly are identical again. And so this is the maximum after you have eliminated all symmetries. So this looks quite small, but a very important observation is that this is not the size of the game tree. This is the number of states. But the number of possible games that you can play that involves all these games is still more than 26,000. So I've reported that number just to make you aware of what's the relation between the number of possible reachable states and the number of games, because the size of the game tree relates to the number of games that you can play. And the reason that there's such a huge difference is because the very same states can occur multiple times by following different strategies, but it will still be a different path in the tree. By the way, I've written it down here that a game is translates to a path in the tree, right? You start with the initial board situation, and then you run down the tree to a leaf node. And that path is playing a game, essentially, from the beginning to the end. So this means if there are roughly 20,000 possible games, that means that we have a search tree with roughly 27,000 paths in that tree. That's still nothing. Obviously, this can be solved by every home computer using alpha beta, and pretty sure even with Minimax. I mean, that number is tiny. So let's get bigger. That's Connect 4. I've already briefly explained the rules. The numbers are much larger. So you see here that there are 10 to the power of 12 times 5, more or less, game states. Although, again, this includes symmetries. So if you eliminate symmetries, the other number will still be a little bit smaller, but that number is still larger. In particular, if you remind yourself, this is the number of states, not the number of games. So the game tree is still much, 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 much larger. I mean, remember, we had the jump from roughly 800 to roughly 27,000, sorry. So the game tree here is still much larger. But yet it was solved actually a very long time ago in 1988, independently by 2 different researchers. But this was not done via search. I didn't read the research paper. I've only read the Wikipedia article, which says it's not search. They used a knowledge-based approach. But you can read the paper. It's published. It's out there. So you can see how they did it. However, quite interestingly, although this number looks really, really high, the Wikipedia article mentions that even this game today can be solved by relying on alpha-beta pruning. So that would be a game, despite its large size, I would argue, can still be solved using alpha-beta pruning. So let's get bigger. Blockers was the assignment a couple of years ago in this lecture. And there you see the board in the background. Every player has 1 color, and the game rule states that you should start in one corner of your choice, placing one of your tiles. and you have to connect your own tiles using certain rules. And the goal is to place as many of your tiles off the board before it gets full. And as you can see from the background color, it's getting too occupied. So not every player will be able to place all his tiles on the board. So you should expand quickly, but you should also defend your area so that the expanding opponents will not capture your area and steal place away from you that you could use for yourself. And that's a huge game. In the beginning, note that all 4 edges are equivalent, right? You can rotate the board. So all edges, they're completely symmetric, doesn't matter. So you have exactly 58 possibilities. You have like 6 tiles, but you can rotate the tiles in different ways. So just placing 6 tiles in one edge leads to 58 different moves for the first player. The second player now has 2 different edges to choose from. It's not 3 edges, because 2 edges are symmetric. Whether you choose the edge on the top left or on the bottom right, doesn't matter, they're symmetric. It only matters whether you choose, let's say, the bottommost edge or the top right edge. They're different. And again, he has 58 moves. So for each of the states above, we have 2 times 58, which is 116 moves. That's for the second player. The third player then only has, again has 2 choices, so again 116. And the third player then only has 1 remaining edge, so only 58 possibilities. But if you look at that game tree here, then you see that even before the first player can do his second turn, we again have 4.5 times 10 to the power of 7 moves. And the entire game of tic-tac-toe was also 4.5 times 10 to the power of 12, so still larger, but that's just the first move, and it gets more and more. So that's really a huge game. 2 more examples and then more content. Chess has, according to some estimates, a maximum number of 10 to the power of 55 states, and some estimates on the lower limits on the game tree size, so now we are talking about the actual game tree, is 10 to the power of 123. And that's quite a huge number if, for instance, you consider that the estimate of the number of atoms in the observable universe is just 10 to the power of 80. So that's just insanely huge. There are more conservative estimates which estimate the number of reasonable states to be only, the game tree based on reasonable moves to be 10 to the power of 40. But it's not really clear whether this estimate is reasonable, because this more conservative estimate was based on the assumption that every game situation has only 3 reasonable moves and all the rest would just be absurd. And I believe this is way too low. Also, it could be that there are moves which we humans regard obviously bad, but maybe if you just look deeply enough, then it might turn out good. It's maybe just an unconventional move. So I guess we have to be careful when we talk about useful moves. I think it's more an objective measure to take a look at the entire game tree. So I guess the 10 to the power of 123 gives a more realistic impression on the complexity of the game. Last example is Go, which was always regarded like the great final challenge of game AI, because the state space is just insanely huge. Because in that game, you see it in the background, you have a board 19 times 19, and on every position in that board, you can place your own tile, which is black or white, depending on which player you are. So just because of the insane amount of number of possible board configurations, the number of possible games is really, really, really large. So you can actually compute the exact number of positions, and just the number of positions is 2 times 10 to the power of 170. And yeah, very below you see the number of actual games that you can play. So clearly there's no chance of representing the entire game tree. That just cannot be represented. Yeah. So what do we do with these large games? Clearly, we simply cannot compute the entire game tree. So what we do instead is that we compute the game tree up to a certain depth, where we have a node which is not yet a terminal. And then we apply heuristic. So we estimate the outcome of the game. We don't find it by exploring the entire tree, but we estimate the outcome of the current board without looking further, just by saying, that's the current situation, I guess that's good, or I guess, no, that's very bad. And I do this in the example of chess, where every beginner, you will learn that in the first session, gets this rule of thumb, that every pawn is worth 1 point, every knight and bishop is 3, every rook is 5, every queen is 9. So you just sum this up. And if you do that, then the current board position will tell you that the black player has 7 points, the white player has 6 points, so black is slightly leading. And the rule of thumb is, once you lead by 3 points and you don't make like an obvious mistake, then you're winning. So lead by 3 points and you win. That's the rule of thumb based on these estimates. There is a problem with this example, but I go to this later. The second possibility towards handcrafted heuristics is learned heuristics. And this is done in machine learning, where essentially you have a number of features, and you learn, based on machine learning, the weights for those features. And if you look closely, you see that this is actually what we've done in chess. Because you can regard the feature f1 as the number of pawns in the current state, and the weight is 1. The second feature is the number of knights, and the weight is 3. So that's essentially exactly the same like the thing we have done in chess by hand. But this is how you can do it with machine learning, so you learn the weights. You just need to find good features. And another possibility is actually a different algorithm. That's Monte Carlo tree search, which is kind of similar to Minimax. But what it does is that you choose the node to expand, and based on the best outcome that you have derived in previous iterations, after you have selected the best node according to the strategies of all players, you expand the leaf node that you get by following your marked edges. And then, because they are new, you have a new node that you didn't see before. And what you do then is you simulate the game. So everybody makes more or less random moves, and you simulate the game towards the very end. And then you get a final outcome, because you've played the game towards the end. And this final outcome is then used as a heuristic value for that node where you were. And then you propagate this upwards again. And, oh, I'm sorry, what just happened? Sorry, I have hit my touchpad. So this is what you're doing in the Monte Carlo tree search. So you're iteratively expanding a node according to your best strategies and simulating a game by making random decisions until you find a terminal game outcome and use that outcome for your heuristic estimates. But I mean, clearly there's more to Monte Carlo tree search. There are complete lectures about that algorithm. And I recommend that YouTube video to you, which is an actual lecture, which I really enjoyed. It's really good. It really explains the algorithm in a good way. So it's definitely worth taking a look at this if you're interested in Monte Carlo tree search, which is really an important algorithm for solving games. So one question is when to use heuristics. When do we estimate how good something is? And we do that, or, well, that's not really clear. I just want to emphasize that there is a problem on when to decide this. And this is what you see in this horizon problem here, or in that, it's called horizon problem, and you see it in the current board game. Because when you play chess, you know that the leftmost, topmost right pawn in the next move can move to the topmost row, and it will be transformed into a queen, which is worth 9 and not just 1. So evaluating this board is a problem because the heuristic is not stable. Just one turn later, the situation will be completely different. And that's the horizon problem, that you need to figure out when to evaluate your current board with a heuristic, because it can be that just one turn later, it will be completely different. So now I want to show you, just for those of you who didn't read it yet in Piazza, what the current assignment will be. That's about Zuru of the Seas, and I'm just going to show 2 quick videos, 2 minutes. We start with Zuru, which is essentially the underlying game mechanics. It's not the game that you have to model, but it shows the underlying game mechanics.
I'm the Rules Girl, and this is Zuru, a tile placement game of pathfinding for 2 to 8 players. In Zuru, players control pawns, following the path laid out in front of them. The goal of the game is to win, and you win by being the last player standing, accomplished by driving other players' pawns into the edge of the map. On your turn, you'll place a tile connected to your pawn's path, then move your pawn and any other pawns to the end of their extended path. If your pawn reaches the edge of the map or collides with another pawn, you're eliminated and shuffle your hand back into the tile deck. At the end of a turn, players draw back up to 3 tiles, if possible. If you need to draw but can't, claim the dragon token. Now when the draw pile is replenished, you'll be the first in line to draw a tile. And that's the game. When only 1 pawn is left, that player wins. Ready to play? Each player draws 3 tiles. Starting with the oldest player, everyone chooses a notch on the edge of the board to place their pawn. The oldest player goes first. If you like Zuru.
So yeah, that's like the underlying game mechanics of Zuru of the Seas. And what you've already seen is that there is also partial observability involved, because your opponents will place tiles, but you don't see which tiles they are. You only see your own. And now just 1 minute of the actual game that you have to model and to solve, or to model an AI for, which is Zuru of the Seas.
Let me show you what I mean about what I just described. So let's say on my turn I rolled the dice, and I rolled a 6, 7, or 8, like that. So I rolled an 8. That's not good because the monsters are going to move. So I roll the die. Let's pretend this rolled a 1, like that. And let's pretend I'm the yellow player who is the active player. So this monster is going to shift down like this. And since it's my turn and I have to play one of these wake tiles, I can't because this monster's in the way. So I'm immediately eliminated. So my ship's dead. However, the green player right here is safe because the monster still has time to move out of its way. So let's say on the next player's turn, they roll the die to see if it wakes up. And let's pretend it does. Let's say again, it goes a 1. Well, the green player is safe now. It's out of the way.
Okay, so that was really just a short teaser to show you what game the assignment will be about. If there are questions about this, I hope I can answer it after this lecture, and otherwise will also be available via the forum. By the way, regarding the rules, if you also enjoy watching these YouTube videos, don't forget that you have to adhere the rules that were officially given by Steve on the web pages. Because if there were some changes, you really need to adhere the ones that they specify, not anything you find on YouTube or somewhere else. So to quickly give you an overview of game achievements, in 1959, Arthur Samuel develops a checkers playing program. Checkers is the game you see on the top right. And Arthur Samuel is also credited as being one of the co-developers of alpha-beta pruning. And the algorithm here uses or exploits that the game AI improves itself by playing against itself all over and over again. So in 1997, Garry Kasparov was beaten in the game of chess by a chess computer. That was also quite big news, obviously. And in 2007, the game of checkers that you see on the top right was solved. Remember, solved means we know the game theoretic outcome. We know whether or not we can enforce a win or not. In 2011, Watson wins Jeopardy. And that was quite interesting because it's a very, very hard problem because it requires language understanding. So here you are given a response and you have to find the respective answer for that. So it's given some response and the correct answer might be, what is Toronto? And yeah, this was obviously done using a lot of machine learning. And in 2015, reinforcement learning algorithm learned to play Atari games completely from scratch. So that really only had the available, the game rules available and the pixels, the graphics, nothing else. And it learned playing these games really, really, really well. And quite astonishingly, in 2016, DeepMind's AlphaGo beats Lee Sedol, which was a 9-dan Go player, so one of the best players in the world. He was beaten 4-1. And this is actually based on machine learning, but also on the Monte Carlo algorithm that I've introduced very briefly. And finally, in 2017, there was a new version, AlphaZero, which was much, much, much better than AlphaGo. And it also learned to play chess and shogi. And the interesting thing about that is that AlphaZero did only play against itself, whereas its predecessor, AlphaGo, was fed by games from humans. But yeah, you can read this up. So that's from me. Thanks for listening.
Great. Now, do we have questions? If you have questions, please put them out on the chat. We've got time for one or two quick questions. So I'm keen to see some questions for Pascal.
Yeah, maybe if there are more, maybe, I don't know, you can also post them via the forum later on.
Well, we're just getting messages of thanks at this point.
Oh, that's fine too.
All right. In that case, if you have questions, more questions, then oh, hang on. All right. Here's a good question. Do you have any suggestions for resources we should look at for AIs for games with more than 2 players?
Oh, sadly, I have to say no. I would have to look that up on my own. But you can ask this question on you can ask this question on the forum, so I can answer it publicly. But with regards to the assignment, I think it's restricted to 2 players.
There's an extension where they can do whatever they like, and one possibility is they could make it multiplayer. But there's an open-ended extension on task 13. So one possibility is they would make it multiplayer.
Yeah, so I would have to look this up. So if you post the question in the forum, I will answer it in the forum.
And I've got one other last question, perhaps. It's a fairly open-ended one. It just says, how would you suggest dealing with the limited information in Zuru?
Yeah, that's a hard question. I guess it's also always the question on whether you want to choose the Monte Carlo approach on simulating a game outcome, or whether you want to come up with heuristics for the current board. And I'm not really sure what works better in that game. Maybe you might want to try both. So I guess maybe it really makes sense in that game to just to apply to finish the game essentially, like Monte Carlo Research does, by applying a couple of moves, random moves, and see whether or not it will lead to a win or not. I don't know, I have a hunch that this could work in that game, but I really had to try this out on my own. And otherwise, it's like in Minimax, right? You're computing the expected probability. That's what you could do.
One approach that some students have used successfully for some games in the past, I don't know if it's going to work here, was to take a machine learning approach. So once you have a game that can play correct moves, then you just play lots and lots and lots and lots of games with randomized moves or semi-randomized moves or some heuristic and try to gather some information from that, which would then further guide the game. So whether or not that would work here is another matter, and whether or not you've got the compute power to do that is another matter. All right, I think with that we've just passed 2. We've just finished our hour. We'll say thank you to Pascal. It was a great talk, and Pascal is on Piazza, so there is a chance to ask some questions. Oh wait, there's one really nice question there. I'll just ask you this one last question. It says, have you got a favorite book about computer science which really helped you to become a better programmer?
I'm actually more into theory than into programming. So actually, whenever I'm working on a paper which is really heavy on the empirical stuff, I try to get it done by colleagues. I'm really more interested in proving theoretical properties. I have a couple of books that I like, but they're mostly concerned with planning in particular.
Do you have any that are not about programming that you might recommend that are computer science books?
I can put this to the forum.
Yeah, maybe it's getting too narrow. All right. Thanks very much for the talk. That was great. People are saying thank you on the forum. We really appreciate you taking the time to give a guest lecture like this. It takes a lot of work to give a one-off lecture like this, so I am certainly extremely appreciative. And hopefully everyone in the class realizes the level of expertise that Pascal has is far greater than what I can offer you as a programming languages person. So thank you again, Pascal, and we'll catch everyone else on Monday. All right.
Okay.
Bye.